Alright, welcome back. So this is the last lecture. We looked at an algebraic comparison of R and C. Then we started calculus. We did differential calculus the last time. And we are going to end with integral calculus. Yeah. So recap. In the last lecture, we discussed continuity in the multivariable sense for real numbers, in the sense that if you take a real valued function from Rn to Rm, it's said to be continuous if f of x naught minus f of x can be as small as we want by making sure x naught is close enough to x. Yeah. And we saw this the same as complex valued continuity, so there's no essential difference. However, multivariable continuity, that is continuity in two variables, is different from being continuous in each variable separately. Okay, this is a crucial difference. Right. But we saw that when it came to differentiability, real differentiability, first of all, in more than one variable, this is itself complicated. This is basically f of a plus h, the linear approximation being true. The partial derivatives exist, and this goes to 0. Yeah. Complex differentiability is very similar to our familiar difference quotient definition. Right? This implies real differentiability, but the other way is not true. And this in fact implies that f is smooth. Okay? As I told you. So real and complex differentiability are very, when I say complex differentiable, I mean holomorphic. Okay? You might think that, all right, if you take the best possible real functions, that is real analytic functions. What are real analytic functions? Functions that are differentiable as many times as you want, and around every point in their domain, there is a power series expansion for the function. Namely, the Taylor's series converges to the function in some domain around the point. Complex analytic is more or less the same thing, except these two notions are very different. In particular, every holomorphic function is complex analytic and vice versa. That's not true for real differentiable functions. And even real analytic functions obey very different properties from complex analytic ones. In particular, if you take 1 by 1 plus x squared, it's bounded and real analytic throughout R, but it's not a constant. In complex analysis, that is not allowed. Yeah. There are various other such properties. All right, so let's go to integration. So the Riemann integral can be used to make sense of the integral from a to b f of x dx whenever f is a continuous function. Okay. Not everything is integrable, so for simplicity, let's assume f is continuous. Okay. Given a continuously differentiable path, this is common terminology, it's also written as C1. What this means is that, if you have a function, what's a path in Rn? Something like this, right? It's parameterized by time. So at time t equals 0, you're here. At t equals, say, 1, you're here, right? And this function, gamma, from 0, 1 to Rn, this is required to be C1, as in gamma prime is assumed to exist and gamma prime is continuous. Okay? For convenience, we make these assumptions. You can weaken them, but it's not worth it for our discussion. Yeah. So given a continuously differentiable path, you can define the line integral of a continuous function. So what does the line integral mean? This is supposed to be like the following, if you're happy with physics. This is like the density. Suppose you have a rod, and the rod is shaped in a very weird manner. Suppose it's bent. If I give you the densities, it varies from point to point. Okay, this is like the mass of the rod, right? Density times the little amount of length. You add up all these, you get the mass, right? So this is simply f of gamma of t. Well, naively speaking, this is simply gamma prime t dt. That's what I've written here. Yeah. So, given a complex valued function, how can you define its integral? Just like Riemann integral, you can define a complex line integral. You can talk about the integral of a complex valued function along a curve. Okay, that's what makes sense for it. You can also talk about the integral of a complex valued function in a domain, but that's less useful. So if given a complex curve, you can talk of f of gamma of t, gamma prime t dt, right? Already you see the problem is if you take integration, the reason this is very different from this is because in the complex plane you have geometry, right? You can have lots of curves, you can have lots of things to integrate over. On a real line, it's quite boring. You just have one thing to do here, integrate only along the line, right? So that's what makes complex analysis a little richer, but that's not the main point. Okay. The key point here is please bear in mind that these two are complex numbers and you're multiplying them in the sense of complex numbers. Okay, so it's very different from just taking R2. Again, you're using complex multiplication. So in real Riemann integration, there's a familiar, very standard theorem, integral from a to b, f of x dx. What does that mean? In the language of areas, it's simply this positive area plus this negative area plus this positive area. This is of course less than if you make all the areas positive, right? Of course, right? So this is almost, yeah, it's quite straightforward to prove. It's slightly more tricky, but one can prove that basically if you want to write it in this language, this is less than integral gamma mod f of z mod dz. So it's very similar to this, except this is a little harder to prove. Why is it harder to prove? Because if f is u plus ib, what is the left hand side? It is the integral over gamma of u square plus integral over gamma of v square. What's the right hand side? Suppose f times dz. Well, let's say f of gamma of t, gamma prime of t. Let us call this as u plus iv. Okay, u dt squared and v dt squared. On the other hand, the right hand side is square root of u square plus v square dt from a to b. Sorry, let's write it as a to b. Why is it that this is larger than this? This is not entirely trivial to prove. I invite you to try to prove it yourself. One way is the following, that you assume that u square plus v square is 1. You reduce it to this case and try to use the Cauchy-Schwarz inequality. Okay, please try to do it. It's not a trivial thing. It requires some work. So if I were you, I would emphasize this to a student, that while these two look very similar, this is a little harder to prove than this. Okay. All right. So what do you do with integration? The main theorem is a fundamental theorem of calculus. That is something that relates differentiation and integration, right? After all, there's a lot of debate these days about who discovered calculus, etc. The key contribution of Newton and Leibniz is this, the general form of the fundamental theorem of calculus. It's generality. Right? that distinguishes their contribution from anyone who came before them. Till then, calculus was not on a general footing. Only special cases were discovered in an ad hoc manner. Yeah. Anyway, so what is the fundamental theorem of calculus? So if you take a real function, that is a function from, let's say, AB to R, and if f is continuous on its domain, then you can define a new function, capital F of x, as integral from a to x f of t dt. First of all, because f is continuous, you can talk about its Riemann integral. Makes sense. Now, capital F of x is actually differentiable, and capital F prime is f of x. Okay? For this, by the way, you need f to be continuous. You need some requirement on f. In particular, continuity is good enough. So you can't make do without it. This is the first fundamental theorem of calculus, or maybe the second one. I keep forgetting which number is which. But the other fundamental theorem of calculus is if there is an antiderivative, namely if f of x is capital F prime x, where capital F is some function, and f is Riemann integrable, otherwise you can't talk of its integral, then the integral from a to b f of x dx is f of b minus f of a. Right? So these are the famous fundamental theorems of calculus. For a complex function, ideally we would like a similar statement, right? What statement would be like, if f is a holomorphic function, integral from a to, suppose, z naught to z, f of z dz, along what path? Take any path. You define it to be a new complex function. Hopefully that is holomorphic, and hopefully it is an antiderivative, right? This is what we would ideally like. Unfortunately, this notion, integral a to b f of z dz, depends on what path you take to go from a to b. You can get different answers, even if f is holomorphic, mind you. Even if f is holomorphic. For example, if you take 1 by z, 1 by z is holomorphic everywhere except z equals 0, where it's not defined. And you take the points -1 and +1, these two real points. Namely, you take, so you're not allowed to talk about this point, you're allowed to talk about these two. You have many paths leading from here to here. One is through the upper hemisphere, one is through the lower hemisphere. I mean, not hemisphere, semicircle, right? If you compute the integral along this and along this, you get different answers. Why? You can compute it on your own. Just take z equals e raised to I theta to compute this one, and take z equals e raised to, yeah, same thing. You can take z of theta is this, where theta is between, in this case, pi and 2 pi. The other one you can take z as e raised to minus I theta, if you will, where theta is between 0 and pi. You can compute this, you get different answers, right? I mean, of course, we know that's because there's a pole here, right? So unfortunately, even if f is holomorphic, this is still a problem, right? This whole concept is still problematic. Thankfully, we have a theorem in this regard. This is the Cauchy-Gursa theorem. If f is holomorphic on a triangle T, what does that mean? So you have a triangle T, and f is holomorphic throughout the triangle, then its integral over the boundary of the triangle is 0. How does that help? Well, if you want to go from this point to this point like this or like this, you get the same answer, right? This might not seem like much, right? I mean, what the hell, we are just proving that this is the case on a triangle, but it's not so straightforward. Huh? Gursa's proof is quite beautiful and non-trivial. Cauchy proved the same thing, assuming that f is C1. Okay? But you don't need that. You just need it to be holomorphic. That's good enough to prove this. That's the point. Okay. In fact, you might think that there's a very special case of some theorem, but there's this theorem, Moreira's theorem, that shows that if this is true for all triangles in your domain, then F is actually holomorphic. Okay. What that means is if you take uh, every triangle in your domain and if the integral is 0, then F is holomorphic. And F has to be continuous for this Moreira theorem. But anyway, so we have one nice theorem. Okay. Using this theorem, one can prove, not exactly using this theorem, in some sense, maybe you can say using this theorem, one can prove the Cauchy integral theorem. That is, uh, if gamma is a simple closed curve. Now this is, so that's the problem, when you talk about Cauchy's integral theorem, integral formula, etc. You cannot do away with without a little bit of topology or geometry to state them in their full level of generality. Even Rudin, hardcore analysis Rudin gives up at this point. Point is, if you want to state one general version of this Cauchy, uh, Cauchy's integral theorem, you have to consider curves of this type, namely not curves like this, curves like this. So they're not allowed to have self-intersections other than just at one point. So they're simple closed. And there is this theorem called the Jordan curve theorem that shows that every simple closed curve has an inside and an outside. Now that also seems like an obvious silly point, but it's not. Okay, it requires a lot of work to prove this Jordan curve theorem. Okay, right. Okay, so if you have a simple closed curve such that f is holomorphic inside this curve, on the inside if it's holomorphic, then its integral is 0. Okay. All right. So how does it help to know that the integral is 0? So if, for example, if f is holomorphic on a disk, and you take any 2 points in the disk and you take any 2 paths, the integral is the same. Why? Because if you take 2 paths, then you can concatenate the paths. I mean, you can go along one path and return back along the other path. So along this this whole path, you can say, well, if you put in a little bit of effort, this path need not be a simple closed curve, but you can break it up into simple closed curves. Anyway, I don't want to get into it, but on paper, using this theorem, you can prove that the integral is independent of the path. Okay. So notice that something as simple as the fundamental theorem of calculus is already very tricky in the complex setting. So in this sense, maybe real functions shine in this respect. But the fact that it's tricky can be used to our advantage, as we'll see soon. Okay. All right. So in such a case where this sort of a situation holds, you can define now f of z as z0 to z along any path f of w to w. Thankfully, this is a holomorphic function and it's an antiderivative. So in this case, the fundamental theorem of calculus holds. The other fundamental theorem of calculus, if a holomorphic function f exists so that f prime of z is f of z, then this is path independent. Okay, then this is f of b minus f of a. The other way is fine, not a problem. Okay, why is that fine? Please try to prove it on your own. So related to this circle of ideas is this very all-important Cauchy integral formula. And that's, suppose D is a disk centered at Z0. So I'm going to state a very special case. All right. I'm going to state a special case and move on. Let's say this of radius R. Point is, you can talk of a more general formula. I mean, whatever I'm going to state right now, while I am looking at a disk, there's a disk and there's the boundary of a disk. It's a circle. The center is Z0, radius R. You can take any reasonable nice domain. Maybe I want to make this nicer. Maybe. If you take any reasonable domain which is simply connected, what that means, if I take any curve, it can be shrunk continuously to a point. For example, what's not allowed is this. Because if I take this curve and I attempt to shrink it to a point, whoops, there's a problem here. Right? So if you take any reasonably nice domain, the following formula holds. F of z0 is 1 over 2 pi I integral f of z dz by z minus z0 on the boundary. Okay. This formula is very closely related to Cauchy's integral formula. I mean Cauchy's theorem that we stated earlier. Not very different. Anyway, the bottom line is, you see this here? You can write this as 1 over z times 1 minus z naught divided by z. And you can write a geometric series which converges when mod z naught, for instance, is less than mod z, right? Using this geometric series, so you can write this as a series, and you can use some justification to take that to interchange limits and summation. For instance, you can use uniform convergence. You can now prove that holomorphic functions are complex analytic. Basically, if you write this as a series, f of z0 is a power series in z0, roughly speaking. Okay, it requires a little bit of justification, but can be done. Okay, so the Cauchy integral formula can allows you to prove this all-important fact, and therefore holomorphic functions are smooth, right? So that's the point. Now, the Cauchy integral formula allows you to do many other beautiful and interesting things. Just this special case is good enough for many things, by the way. Just this formula. Not even with all these fancy words. In fact, if I remember right, one textbook, I think Stein and Shakarichi, someone's textbook, does a lot of complex analysis with just the simplest case of Cauchy integral formula. Anyway, now the point is, if you look at this Cauchy integral formula, you can differentiate on both sides with respect to z0, right? Now, of course, taking the derivative inside the integral sign is a tricky business. I think most it's probably likely that in many undergraduate courses one skips all the work. That is fine as long as you tell your students that you are skipping the work, that this is not a straightforward thing. The point is, when you differentiate inside the integral sign, the derivative of 1 by z minus z0 is minus 1. Over, it's not minus, it's just 1 over z minus z0 square, right? So f prime z0 has a nice formula. It's integral f of z dz by z minus z0 square. Now you can take mod on both sides and use the integration estimates to show that, okay, let me actually do it for you. Let's actually do this. So mod f of z0 is less than 1 by 2 pi mod f of z mod dz over mod z minus z naught. So you take the maximum value outside and you integrate. Sorry, f square. F prime is f square and you integrate this, yeah, on the circle. So when you do that, you get this estimate. Okay, hopefully I haven't made any silly errors, but whatever it is, this estimate is inversely proportional to the radius of the disk. So in particular, the point is, if you have a bound on f, you have a bound on the derivative. Now, this should be very shocking to you. If just because a function is bounded doesn't mean its derivative is bounded, right? The function can wiggle as much as you want, right? Just because it's bounded doesn't mean its derivative is. Right. So as a consequence, if f is entire, which means it's an analytic function on all of C, and if it is bounded, then you can write this formula. This numerator is bounded by some number, and this r can be anything you feel like. So f prime of z naught is 0 for all z naught, so f is a constant. So this is Liouville's theorem, and it's a very trivial consequence of the Cauchy integral formula. Okay. Now we can prove the fundamental theorem of algebra, which illustrates an important difference between real and complex numbers. So if a non-constant, of course constant polynomials don't have roots, but if a non-constant polynomial doesn't have any complex roots, then of course 1 divided by p of z is a holomorphic function for all z, right? It's an entire holomorphic function. It's an entire function because p of z never vanishes, so 1 by p of z is always differentiable in a complex sense. Now it is bounded to. How do you prove that? I leave it as an exercise to you. The fastest way to do this is the following. If you take p of z, it's something like some non-zero complex numbers times z raised to n plus lower order terms, right? So when z is very large, z raised to n dominates the other pieces. So p of z is roughly like mod z raised to n. But when z is small, 1 by p of z is bounded anyway because a continuous function is bounded on a compact set. So roughly that's the reason why it is bounded. Okay. You can do it for your students, by the way. So it's a useful exercise in the triangle inequality. And hence it's a constant, so it's a contradiction, right? All right, so this finishes our series of lectures. I'll just make a few comments about what lies beyond. So many real integrals, like this very innocent looking integral 0 to infinity sine x by x dx. By the way, this is an improper integral. It is not, if you take the mod of this, it's no longer integrable. The integral doesn't make sense. But as such, it does, if you interpret it correctly. You have to take the limit at 0 and you have to take a limit at infinity too. So many real integrals of this sort can be evaluated using Cauchy's integral formula, okay, by choosing the right contour to integrate and the right function. Okay. So it's a real integral. I could have given you this as a problem without ever talking about complex analysis, but the easiest way to do it is using complex analysis. Shockingly, natural numbers are a special case of real numbers. And you would think that, first of all, real analysis is itself not going to be helpful when you study natural numbers, right? But shockingly, many things about natural numbers can be proved using complex analysis. So this branch is called analytic number theory. And if you take more than one complex variable, like f of z1, z2, functions like that, that is a whole different ball game in its own right. Just like if you take real analysis, multivariable calculus is far more complicated than single variable calculus. I mean, there are many surprises, Just like that, several complex variables is far more complicated than one complex variable. But these are more advanced things, but you can always point these out to your students. So I hope this has been helpful. Thank you for joining.